I guess we'll get started. I'm supposed to give read anything up here. Recap of day one, and introduction to day two. Okay, well, the short recap is yesterday we generally were just talking about ideas of what we all think the circulation and circulation changes are in the subarctic seas, and that's where our talks were focused. And I thought it was great. I think the goal is or the objective was to assess the state of knowledge of Arctic Ocean circulation. And I don't think we did that assessment, but we started the discussion, and that it was, I think, very successful. I think one of the things I noticed that I really look at as a success was that there were a lot of early career folks and students, and I think, and I certainly hope they felt free to enter into the discussion, because they're going to be the people that kind of carry that forward. So I was glad to see the energy and enthusiasm for the discussions. And in our group, our breakout group, things kind of were free-ranging. Got quickly into sort of processes. Eddies came up for discussion. There was a bunch of discussion of that and what we needed to resolve and what the role of eddies of different resolution were involved in modeling. Got into kind of discussions of how you think about or represent ice in models, things of that nature. So I didn't feel like our group really homed in on, oh, here's this notion of circulation or that, and but I don't know that that's critical, because it's more a process of starting the discussion. So. And Mary Louise, can you say a couple of words about your breakout group?
Sam. Sure. Yeah, this is Mary Louise. So we talked about, well, we had also a pretty wandering discussion, I think, but we talked about how well the large-scale circulation is represented in models, for one. And this sort of stemmed from John Toole's presentation, where he was talking about the representation of the directionality of the Atlantic water circulation in OSTI, and kind of speculating on reasons why that might be and what we can do to improve this or understand model shortcomings better and constrain the models with observations. Stratification came up a lot, and how this influences both the circulation as well as vertical fluxes and everything associated with that. We talked a lot about the large-scale circulation of sea ice and how this has changed under reduced sea ice cover and also probably swifter ocean currents. And this idea came up that this Rigor et al. Paper, this 2002 paper that characterizes the modes of sea ice circulation, we thought it would be good to revisit this now, 20 years, and examine this in the context of the most, the past 2 decades of data. We talked about a few other things, but we'll report out, I think, on Friday.
Sure,
So that's
yeah.
in general. And I may have forgotten a bunch of stuff too. So thanks.
Oh, that was great. Dimitri was the other breakout person, or in-person breakout person.
Yeah, we also had a very productive discussion, and I would like to thank everyone who participated in the discussion, and especially Stephanie for taking very careful notes. We will summarize our conclusions on Thursday, but just to give an overview, we discussed the character of the Arctic Ocean surface circulation change, and we talked about anticyclonic versus cyclonic indices. So actually, this idea came from Jamie's presentation. We know that there is an index which characterizes the intensity of the anticyclonic circulation based on the Beaufort Gyre SSH gradient used by Andrei Proshtinsky and Mark Johnson. And we are not sure if something like this exists for the cyclonic circulation to characterize the intensity of the cyclonic circulation in the Eurasian basin. Then we discussed the role of the transpolar drift. How much of a barrier is it? According to some model studies, the transpolar drift acts as a barrier, and the water masses from Eurasian part of the Arctic Ocean doesn't seem really to cross the transpolar drift, but instead they follow with the transpolar drift to the North Atlantic. And the same happens with the water masses and on the side of the Canada basin. They kind of do not cross the transpolar drift, but carry it to the North Atlantic with the transpolar drift. So we think it would be very useful to characterize the variability of the transpolar drift and also assess the role of the transpolar drift. Does it act as a barrier, and how much the cross flow occurs between the two basins across the drift. And yeah, we talked on some other questions outlined in the discussion questions. We talked about the impact of the changes in the Arctic Ocean circulation, both in the upper layers and in the deeper layers. And we think there is lack of understanding how they are connected or related. And I think we don't know much about deep circulation. What drives deep circulation? Does it change? And etc. And yeah, we also talked about the possible changes in the storm events in the Arctic Ocean. And many more things. And yeah, we'll summarize on Thursday.
Oh, yeah.
Yeah.
That sounds great. And John, rating the
Sure. We lost a lot
John,
of.
you,
Yeah, I'm here.
are you there?
Yes. Can you not hear me?
We're working on it.
1, 2, 3.
There you are, John. We can hear you.
Okay. Hey. So we lost a lot of our online participants yesterday evening, probably due to the time zones. So we had a sort of a diffuse discussion of the questions regarding the character of the Arctic surface circulation variability. That's very much a question of the time scale of interest, right? You have short period variability that is probably projects onto topographic waves. There's instabilities of the major currents. That's sort of maybe a monthly or 2-week monthly time scale kind of thing. There's seasonal variations, both locally forced and as well as some remote forcing that may be gets communicated throughout the Arctic either as an advective process, which is fairly long time scale, or maybe a planetary wave communication route that's faster. And then interannually, I gotta say, I don't think we know what the patterns of surface current variations are. We have a sort of the EWG record, which we really don't have a good feel for how that was created, what the data density actually supports. A recent altimetric record is more spatially consistent. That is, as Jamie showed us, has patterns. Whether those patterns exist on decadal timescale, I don't think we know. This question about the character of the surface circulation affecting the deeper circulation, I don't think is a reasonable question. The ocean is forced at the surface, either locally or remotely, and that forcing generates the surface circulation as well as the subsurface circulation. And in grad school we all did the projection of dynamical modes, usually a flat bottom constant n squared modes, which are easy to solve analytically. There's just sines and cosines in the vertical. So that's one way that surface forcing manifests and projects onto deeper circulation, but it's not obvious that the ocean actually has a series of sort of dominant vertical modal behavior. And it may be that in different regions, the dominant vertical structure is different. Maybe the sloping bottom modes, like Peter Rines first talked about, and Joe Lacasse more recently, maybe those things are more relevant than a flat bottom mode. I don't think we know. So yeah, I'm still trying to put together a concise description of what we talked about last night, and I'm still struggling with it. So we'll see on Thursday if I can be coherent.
Okay. Well, I think we have to, I guess we've got 5 minutes. I think we're kind of ready about today. Today, we're going to talk about observations mainly. Of course, these things all get mixed. We talked about observations yesterday too, but today I think our thinking wants to be a little bit more towards the what can we do, and what have we been doing, and what do we need to do better or more of in the future. So it's a little bit a shift in the rather than a statement of what we think things are doing now to here's what we're capable of doing now and what we want to do in the future. So that's a fair description. Our first speaker after Ignatius. Sorry, it's Ignatius. There he is. Okay. And Ignatius will talk about what are the capabilities gaps in ongoing and planned in-situ observational programs. General title.
So for those of you who don't know me, I'm Ignatius Rigor. I'm a research scientist at the Polar Science Center here at the University of Washington. I study mostly sea ice, and I coordinate the International Arctic Buoy Program. This talk and a lot of what we do would not be possible without the collaborations and participation of a lot of the members of the IABP. So the program as a whole basically deploys buoys, in-situ buoys on the Arctic Ocean. In the far right or far left, during spring, we'll land on the sea ice using aircraft and helicopters and planes. In the upper left corner, this is a deployment we did in March of this year. There's a little small buoy next to the tripod that people are working on. That's our basic ice ball. It measures air pressure, temperature, GPS, and it reports by iridium. The tripod buoy is basically a webcam, and so we could look at what's going on the ice and pictures as often as we'd like. And then on just off the picture, we're deploying a nice mass balance buoy, a light version of what Don Perovich and others at Krell deploy. In the lower picture, it's Jamie's dynamic ocean topography buoy. This is a deployment we did in 2019 using snowmobiles out of Utqiagvik. Deployed this buoy in Elson Lagoon, but we'll also go out on the fast ice on the Chukchi side of the Barrow and deploy buoys that'll break away with the fast ice to track them. During summer, the icebreakers will start coming in. In this picture, we show a Woods Hole ice-tethered profiler, the Louis St. Laurent's in the background. There's over 100 of these deployed now, and typically they'll measure temperature and salinity, but they've also been adding other sensors like ADCPs at the bottoms of these things. The next picture is off the back of the Healy. We're deploying a seasonal ice beacon. This is the standard, another standard buoy of the Arctic Buoy Program. Again, it measures air pressure, temperature. This one has a surface temperature sensor and a 2-meter air temperature, which is kind of hard to see behind the string holding the buoy up. And then we'll also fly in C-130s and deploy the network. One of our big assets is the seasonal ice zone reconnaissance surveys. This is a project that Jamie leads up. We basically fly in Coast Guard C-130s out of Kodiak, fly across Alaska to typically the 150 line and deploy buoys and ocean probes on our way out. And then on our way home, we'll go up high and do some drop-sons. So we get profiles of the atmosphere, buoys on the sea ice and surface meteorology, and then profiles in the ocean from AXCTDs and AXCPs. Video shows one of our deployments from a couple years ago. Here we're tagging an ice island with a GPS tracker. This is one of our big seasonal ice beacons. The big yellow cone comes off as soon as it hits the water, and then that temperature mass pops up. These are AXCTDs and AXCPs. Get the ocean profiles. And this last snippet is just us flying up high doing drop-sons. This is an effort led by Axel Schweiger and Zhang Liu. So these Coast Guard flights, we've been doing it for a number of years now, but we're also trying to leverage this DoD collaboration called Ice Paper, International Collaborative Engagement Program for Polar Research. It's basically 7 countries, Arctic nations. Their defense departments are contributing assets to help us do research. And I'll show another slide of that later. And so this Rigor et al. Paper was mentioned yesterday also. Here, the typical situation back when the Arctic Buoy Program was first established is we had a strong Beaufort High and a large Beaufort Gyre. Alan Thorndike and Roger Colony used to joke that we could just deploy buoys along the 150 line and, and that's all we needed to do because the Beaufort Gyre would spread the buoys all over the Arctic Ocean. But the weather patterns have changed and we have more of a situation like 1994 where the transpolar drift is stronger and the buoys are quickly flushed out of the Arctic Ocean within a year or two. It turns out that these changes in circulation are related to the Arctic Oscillation. So during the low AO periods, you have the large Beaufort Gyre, and in the high AO periods, you have a smaller contracted Beaufort Gyre, which may be more intense, and then a transpolar drift stream that sweeps most of the ice out of the Arctic Ocean. So looking at our array last year, this is November 2021, the Arctic buoy program had buoys over most of the Arctic Ocean. It's definitely denser on the Canadian side, but we do have quite a few buoys on the Eurasian side. Step forward to June 2022, this month. This is a couple days ago. Most of those buoys have been swept in the transpolar drift stream away from the Eurasian Arctic and are more concentrated now on the Canadian side or have flushed out of the Arctic Ocean. And so this is a recurring gap in the Arctic observing network that we've been struggling to maintain. We've been lucky enough to have some icebreakers going into the Arctic during the summer, and we've been collaborating with the Arctic and Antarctic Research Institute in St. Petersburg, but that collaboration's in jeopardy right now. So given the loss and the recurring hole on the Arctic Ocean, June Inoue did this study looking at the sea level pressure analyses from different models. The maps turn sideways now, so North America's on the right side instead of down. So on the red blob on the map on the left is basically over the Eurasian Arctic. It shows the variance in sea level pressure from a lot of different models, basically where you have no buoys to constrain the models. The sea level pressure analyses could vary by 2.8 millibars. If you think about this in terms of the geostrophic wind and the transport of heat and moisture, this is a pretty big error in the sea level pressure fields, which propagates to other aspects of our climate studies. And then if you take the map on the right shows what would happen if you just took away all the buoys from the various reanalyses and the models that they ran. And basically, we don't know which way the wind would be blowing. Jamie showed this yesterday. The color map is dynamic height and the first EOF of dynamic ocean topography. And overlaid on that is the density of buoys over the whole record of the International Arctic Buoy Program. Basically, on the Eurasian side, you only have about a 10% chance of finding a buoy in some of the centers of action, whether it's the atmosphere or the ocean. But on the Beaufort side, it's a higher chance of 30 to 60%. So this poses a big problem for how depending on what we're studying, we may or may not have enough data to draw some of the conclusions we want to make. Looking at the ocean side, the stars or the circles are all the IABP buoys, but the stars, the red and blue stars, are the ocean profilers. Red are the ice tethered profilers from Woods Hole. Blue are the up-tempo buoys that Mike Steele talked about yesterday. The bottom line is that we need more observations for the atmosphere, but also in the ocean, in this side of the Arctic Ocean. Some of the ways we've been trying to address this problem is, this US IBP and collaboration with ARI in St. Petersburg. Basically, we'll buy buoys from Marlin Yug in the Ukraine and ship these to ARI, who will turn around and put these on the Russian icebreakers to be deployed on the Eurasian side of the Arctic Ocean. This is the deployments we had planned last year, and we have 8 more buoys remaining from purchases we made last year that hopefully will still be deployed. I'm still not sure I'm allowed to pay for that telemetry for these, but we're working that out. One other option we have is the KV Svalbard quickly went into the Arctic Ocean, given the issues that the fire on the Healy 2020, and they were able to go along the northern sea route and reach the Beaufort Gyre. If we could, again, get another trip of opportunity like this will greatly help our ability to maintain the network on that side. NABOS, Igor Polyakov, I think, had a poster here, but this has been one of the most critical logistics assets that we've had to maintain the network on that side. Last year, they deployed 30 plus buoys on, while they're deploying moorings and retrieving moorings. This is another project that's in jeopardy because of the Ukrainian-Russian war. They were planning to go out in 2023. They've been going out every 2 years, but this is a big issue right now, is whether they'll be able to get to find a boat to help them do this project. The Polar Stern is also another option, but they're, in the short run, they have their cruises planned through 2025. And as this shows, this is the closest we'll get to the deeper side of the Eurasian Arctic. They'll be north of the Laptev Sea, but nothing near the Eurasian East Siberian Sea. And this is the cruise in 2024 near the North Pole, but again, nowhere near the deep holes that we need to cover for oceanography and meteorology. So one last aspect I mentioned, ice paper. This is for the U.S. side, John Woods is taking the lead. But ice paper coordinates defense assets, C-130 ships to go into the Arctic. One of the things we're trying to do is do scissors-like measurements using ice paper coordinated C-130s or C-17s. The red track shows a possible flight emanating from alert to target the green circle. Hopefully we'll be able to do AXCTDs, AXCPs, drop some buoys of various types. There's also a chance that we might refuel mid-flight because this is a pretty long run in a C-130 and a C-17 even. And then Jamie and I have been working to get the Coast Guard to fly in August. Basically, we'll fly the 150 line like we normally do for scissors, but then we'll drop back on Alaska to Barrow and then try to fly towards the Makarov Basin, which is a red line in the middle of the map. We're hoping to have a coordinated U.S. Air Force flight to meet up at that area, but our Air Force assets seem to be diverted to this, to supporting the war. So finally, this is our deployment plans for 2023. We have a lot of assets in the Canadian Arctic, and we have a few on the Eurasian side, but as I mentioned, the US-IBP RE collaborations not going to be possible beyond this year. The ice paper flights by the US Air Force will hopefully happen once we have access to these C-130s again. And then scissors and NABOS. Hopefully the scissors flight happens in August, but the Coast Guard seems to be diverted filling in for where the Air Force has not been able to help. And then the NABOS is also in jeopardy. So quick summary. Many of the changes in climate are centered on the Eurasian sector of the Arctic Ocean. These changes quickly transport buoys away from the Arctic Ocean. Logistics in the area have always been sparse, but will be even sparser given the Ukrainian-Russian war. And so we're hoping to find new options to fill in to sustain the Arctic observing network on that side of the Arctic Ocean, given the enormous gap. In-situ observing systems, logistics area. Thank you.
Okay. Yeah, I think we have time for one or two. See, Mary Louise has her hand up.
Thanks, Ignatius. What's the status of the submarines these days?
That's one of the things on my to-do list when I get back is to talk to the Arctic Icebreaker Coordinating Committee and the Pacific Arctic Group to track down whether we could get one of those icebreakers, another icebreaker to go to that side of the Arctic Ocean. But yeah, the submarines are, they're pretty active still. I think through ice paper, we might be able to leverage a submarine to go into that neighborhood. And we have a lot of small ball buoys that could easily. Yeah, so it's something we're pursuing.
Hi, this is Kat Smith from LANL. I'm wondering, do you think there's a role that modeling can play here to help in terms of determining where best to deploy? I mean, I realize that there are constraints in terms of divergent flows and things like that, but we can put, passive tracers or, profilers type analysis in models. Do you think that could play a role in terms of helping to understand the best ship tracks or places to put buoys or?
Yeah, I think models, like all of our tools have a place in determining where to put observations, best places to deploy buoys or put moorings. So yes, I think they're one of the critical tools in our tool bag.
Has there been that?
There has been some efforts. The trick is, like, for the Arctic Buoy program as a whole, we deploy all kinds of instruments. And so for surface meteorology, we'll need, to capture the gradients in the sea level pressure field, we need a perfect 250 kilometer spacing, which is really tough. But then if you're looking at oceanography, depending on what you're looking for, a Lagrangian ITP might be better, and determining those locations is, might be different than looking at boundary currents where you want a mooring.
Okay. I think we'll move on to our next talk now. Thank you, Ignatius. And we'll save some time for discussion later. Next up is Ron Kowk.
So my name is Ron Kowk. I work on satellites. Spent the last 10 years working on ISAT-2. So I will talk about surface height from of polar ocean from satellite altimetry. Oh, there you go. So where's the?
This advance with the arrow keys, or you could.
Okay. So this is, I'd like to acknowledge my the contributors. I'm not going to go through their names, but some of you are here. For the low latitude oceans and tropical oceans, there have been a number of satellite altimeters that have been used to depict the circulation pattern and the sea level of the tropical oceans and low latitude oceans. But for the Arctic and the polar ocean, basically, and the Southern Ocean, it's difficult for those altimeters to get up there because those low latitude altimeters were tuned to avoid tidal aliasing and and they were reluctant to get up to the higher latitudes to sample the polar oceans. So some years ago, here you go. I don't know, some of you may remember this article. This is after ISAT and before the launch of Cryosat-2 and ISAT-2, some of us got together. This is a white paper submitted to Ocean Observations 2009, where we were advocating satellite altimetry, time variable gravity, and bottom pressure for looking at the Arctic Ocean and the Antarctic. But I think that was opportunity. Basically, that was an advocacy paper submitted so that the space agencies could try to support the satellite missions to look at the polar oceans, and so I don't know what happened to that. I mean, it's been taking a few years, but we've now we have actually a fairly good average mean dynamic topography of the Arctic and Antarctic. So the left picture Jamie has shown, that shows the two dominant circulation patterns in the Arctic, and you can see the tilt from Pacific to the Atlantic very well, and so that's a mean field from 5 years worth of Cryosat data that's merged with the Cryosat polar mode with the low latitude, low resolution mode. And also you can see as well and you can see the range of the topography is about 1.4 meters across from the Pacific to the Atlantic. And in the Southern Ocean, you can see very well the ACC and the Weddell Gyre as well as the Ross Gyre. So this is sort of where we are at in terms of getting a mean field, and obviously from the altimetry, as Jamie's shown, we can get monthly fields patterns over the entire Arctic as well as the Antarctic. So this is just from Cryosat-2. So that's sort of where we're at. We can get variability as well as get the mean field. Now, since I'm a remote sensing guy, I have to tell you a bit about the instrumentation and how impressive they are to actually get to this point here. So this is sort of what I'm going to say. I'm going to say a few words about the available observations, the SSH from two altimetry missions that are in orbit, ISAT-2 and Cryosat-2, and the comparison of the SSH retrievals, because I think those two are two independent altimeters, and they're very different altimeters, and we're going to show you that the two different altimeters are actually getting very, very consistent results. And then there are new altimeters, SWATH. Some of you may have heard of SWATH. SWATH for the low latitudes, they're after eddies, and there's contribution of SWATH to the Arctic and the Southern Oceans, but SWATH is not dedicated to look at anything in the north or the ice-covered ocean. So I think that's something that we can talk about. And then I'll talk about outlooks in terms of where we're at in terms of getting more data. Now, who spelled that word? So identification of sea surface returns from ice-covered ocean. I just want to tell you it's different from conventional altimetry because you have to get, in the presence of ice, we have to, in order to get to the ocean surface, we have to look at the ocean surface in the leads. So so the leads are not very wide. I mean, they vary in range, but most of them are less than 50 meters or so. So in order to get that, we have to be able to look at the scattering separate the scattering of the ice from the separate scattering from the ocean. Now, fortunately, the characteristics of the lead, typically when you're looking at nadir, we get specular returns, very sharp returns from the ocean in the leads, and that provides us a very nice way of separating the ice from the ocean. So also the sampling of the ocean obviously is dependent on how many leads there are and whether there are leads around. At some during certain periods of time when there's significant convergence, especially north of Greenland, there are no leads. And so that doesn't happen very often now. It used to be where you can actually see periods where there are no leads. But so this is sort of how it works with altimetry. We have specular returns, and in fact, we don't need very a large lead to actually get a nice sampling of the ocean surface. So these are the two satellites that are in orbit, one from ESA, CRASAT-2, and one from NASA, ISAT-2. CRASAT-2 was launched in April 2010, and it's a radar altimeter, so we get coverage up to 88 north. Same as ISAT-2. ISAT-2 was launched in 2018, and we get coverage to 88 north as well. So, but ISAT-2 is a multi-beam LiDAR, whereas CRASAT-2 is just a profiling radar. So there are 6 ISAT-2 beams. I'll talk a little bit more about that. So let's see. So typically, the satellite missions that launch these days that are dedicated to the polar oceans over sea ice, they're focused on retrieving freeboard for getting ice thickness. But to do freeboard, is there a pointer here? Basically, from the sea surface, and that's the freeboard that we get. And so we get both the ice surface and the ocean surface. So the sea surface is sort of a byproduct of getting freeboard. So this is CRASAT-2. This is a special radar. I don't expect you to know what delayed Doppler processing is about, but I think the idea is that it's a special processing technique to get to the radar footprint to about 0.3 kilometers by 1.6 kilometers. So that's typical. It's a synthesized footprint so that we can get to the size of the leads that we're looking at. And so for CRASAT-2, it's about 300 meters, but we can, in fact, resolve leads that are narrower than 300 meters because of the specular return. And this has been up since, so we have about 10 years of data from CRASAT-2, actually a bit more. For ISAT, so this is sort of a altimetric profile of the CRASAT altimeter transition from the ice sheet, from the ice shelf, actually, the Ross Ice Shelf, down to the ice edge, you can see, and then the sea surface. So you can see the returns that are very characteristics of a very flat sea surface off, but you can't see the details here. I just want to show you how the altimeter, what the altimetric returns look like. So this is ISAT-2, which is a very impressive altimeter. We have 6 beams separated by, these beam pairs are separated by 3 kilometers, and the footprint, okay, so the impressive part is that the footprint is about 11 meters, and these footprints are separated by 0.7 meters on the ground. So you get a very nice sampling of the surface on the ground for doing sea surface height as well as freeboard. So this is, I'm not going to, that's fine. I'm not going to say anything about. Oh, so this is an ISAT return. The top is an ISAT return all the photons returning from the surface. And you can tell that these are, you can see the spread of photons along the surface from single beam. So after you get ice retrieval, you can tell, I guess what I want to show here, within that box is a very flat surface. And the variability of the surface about 1.8 centimeters. So we get a very high precision rendering of the surface from ISAT-2. Let's see. So this just shows the 6 beams transitioning from thick ice to marginal ice zone from in the LC. So the box shows the area that we're looking at, and you can see the profile, the roughness of the ice as you go from the very thicker ice, rough ice, out towards a relatively thinner and flatter marginal ice zone in toward in the northern Weddell Sea. Okay, so this is so in 2020, the CrowSat-2 and ISAT-2 were lined up closely, I mean, almost co-registered in these orbits that we call in a CryoSat-2 operation and 2 ice operation. Basically, ESA put the CrowSat-2 and ISAT-2 in sort of resonance orbit, and with so at around every 19 orbits, there's a bit of near registration between the 2 orbits, and we use those to evaluate the consistency in the altimetry from the 2 different, from the LiDAR and the radar. And that was a pretty nice contribution from ESA to do that. And we were able to use that to compare the sea surface height from the 2 different orbits, 2 different radars, from the radar and LiDAR, not 2 different radars. So this is sort of the comparison. So these are some very good comparisons that we've seen. The top one, the blue is CrowSat-2, red is ISAT-2, and the difference has been about 2 centimeters in the mean. The correlation is pretty high. So we're pretty happy about that comparison. And then the second one is also pretty good. So you can tell that there's so we have some confidence in the types of heights that we're getting relative to the center mass of the Earth. So these are another more examples, beam 1 and beam 3, and these are pretty high correlations, and the differences are pretty small as well. And there are some differences between the way we've done the corrections, but the variability is we expect a certain amount of variability because some of the geophysical corrections are not the same between the 2 different altimeters. So this just shows you the count of number of samples that go into these fields, and the left one is ISAT-2, the right one is radar. The left one is a little noisier because LiDAR is affected by clouds, and the radar is not affected by clouds, and so they're slightly different. Okay, so I don't think I'm going to. Let's see. So I'll say a few words about this. So this is the dynamic ocean topography this is just from between October 2018 and February 2022. This is on a 25-kilometer field. And you can see these little bumps here are associated with geoid residuals, and the geoid that we're using is an EGM 2008, so there's some residuals there. And these are not circulation features. Okay, so let's see. If we look at the mean field over these two different areas, the yellow area, the Beaufort, as well as the Central Arctic, and compare CrowSat-2 and ISAT-2, those are the correlation between them. They're pretty good. There are some differences, and some of the differences are probably associated with the way we tracked the surface, as well as some of the corrections that we've used that are different, tides, for example, and other things that, and time and space sampling between differences between CrowSat-2 and ISAT-2. So I think I should say a few words about SWAT. So SWAT's going to be launched. SWAT is a new altimeter, and it will have wide swath on both sides of the nadir track. And the track is about, the swath is about 70 kilometers on each side. And for the low latitude oceans, they're after eddies. And I think this is going to be interesting, although it's not going to get up very high into the Arctic, but it will be able to sample Southern Ocean fairly well. Let's see. So I think I'll make some remarks. So right now, we have SSH retrievals from CrowSat-2 and ISAT-2. They're in operation. You can also get SSH data from Altica as well as Sentinel-3. They're both, one's the ESA mission, one's the CNES mission. And for historically, there's MVSat. We can get stuff from MVSat, but I think it's going to take a little bit more work. And we have ISAT, which was operational in 2003 and 2009, and Jamie's shown some of the results from there. ISAT-2 is currently, we have, for those who are interested in looking at SSH, there's SSH data from ISAT over the open and ice-covered ocean starting in 2018, and these are available at NSIDC. So take a look if you're interested. Upcoming, there's SWAT, as I've mentioned, and it'll be launched in 2002, this November. And Crystal, which is another sort of like a CrowSat-2 follow-on, which will be launched in 2030. And that will have a radiometer, and that would be at a high polar orbit, and it'll be more like a low latitude altimeter. The current work with ISAT-2, I think one of the more interesting things that we're looking at is coastal altimetry, getting as close to the coast as possible. And right now, some of the stuff, we have geoid issues and tide issues in near the coast. And I think one of the last note I want to say, if you like SSH and you think it's important for looking at the polar oceans, tell the space agencies, tell ESA, tell NASA, and that's important to get your message that making these observations are important for doing the science that we're interested in. Thank you.
Thanks, Ron. I think we have time for one question.
Thanks, Ron. This is Mary Louise. When you mentioned the geoid residuals, that's a bit concerning when we use dynamic ocean topography. So, and that's different from the sea surface height product, right? That's available online.
Right.
So can you just say a little bit more about how cautious we should be?
I think that we typically, when we calculate circulation, we know the sort of the resolution of the geoids that we're using, and they're much better geoid. We use EGM 2008 is pretty old, and the new geoids will have satellite gravity fields in it, and even though some of the smaller scale features will still be there, so I think what we've there was one paper that was, I forget the name, McAdoo's paper? Yeah, that was recommending that we average the data using a 200 kilometer kernel before to smooth out some of the features those features, the geo features in the DOT.
Thanks.
Show up when you look at changes.
Yeah. So yeah, those geo features are static. And so if you're looking for changes from one time epoch to another, they don't show up. That means the changes are not important. That means the static features are not important. Okay.
Okay. Thank you again, Ron.
Okay, good morning, everyone. Thanks for giving me a chance to give this talk here. This group is very new for me. Normally, I go to a lot of remote sensing meetings. Um, so today I'm talking about the salinity in the Beaufort, Gyre, and Arctic oceans. My name is Subramanyam Bulusu. So first, I would like to acknowledge my graduate student, Sarah Hall. Unfortunately, she could not be here today. And I would like to acknowledge co-authors Jamie Morison. So we published a paper earlier this year in the Remote Sensing Journal. And recently we started working on the Russian shelf using Mike Steele. So I'm showing some slides also on that one. Okay, I'll use this one. Okay. 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 So here I'm using so satellites data and also in situ and ocean models. So first I'm touching with the satellites data. So SMOS, as you know, it was launched in 2009. So we have almost 12 years of data. And SMAP, which was launched in 2015. So OISS is, that is optimal interpolation data, mainly combined with the SMAP and the SMOS. So also we are using the in situ observations, scissors data that is provided by Jamie Morison. So today also in the first talk we saw about that. So we are also using the BGP, Beaufort Gyre Exploration Project data. So here we are considering the EN4 as an in situ because it's all combined with observational data set. So also we are using the multi models, echo, mismatch. Here I'm showing the mismatch only for the Beaufort Gyre region. Though they have the Arctic Ocean also, complete Arctic, and HICOM with the ICE model, and ORS5 and Glorious12 are the reanalysis products. So what I want to show here is, as many of you guys are using the Beaufort Gyre Exploration Project CTD CAS 2012, 2013, 14, 15, 16, 17. We took the data exactly to match for the scissors data. So what I'm showing here is the line, that is the one scissors transect. So we are comparing the scissor transect with these observations. So here you can see where we are stand in the satellite or salinity data sets. So here you can see I took the 2015 September 2015 because that is the year you have the overlap between the SMOS and SMAP. So you can see here, we don't get the full coverage from the satellite salinity. SMOS and SMAP covers only part of the Arctic, And OISS is a combination of SMAP and SMOS, so you will see a little bit, further data set, you can see that. And also inherent, there are some biases are there also between SMOS and SMAP. We'll talk further on that. If you're looking at the models, again, EN4, I'm using like a in-situ observations, echo, mismass, and HICOM. These are the three models, and these are the two reanalysis products. So you can see here, there are also models. Every model has their own biases and all. And later on, I will show you, out of these, all these products we have seen, the ORS5 is a little better when you're using any model, output. And Glorious 12 is a little bit saltier in the Arctic region. So the first few slides, I want to concentrate on the Beaufort Gyre region. So here you can see, SMOS, SMAP, and OISS. So you can see here, SMOS coverage is a little bit better in the Beaufort Gyre region compared with SMAP. But SMAP has a little bit, accurate compared with, SMOS. I will show you also in a few slides. So if you look at the models, echo, mismass, and HICOM, so you can see here there is a big differences in salinity. And also you can see here Glorious 12 is saltier than any of these model outputs, and also HICOM is a little saltier. So the coverage, as I mentioned to you, even though models are covers the entire Arctic, you can run, but the problem is you see the big differences in salinities. So that will also give some errors in the freshwater content and all those things. So here you can see along the scissors transect, if you're comparing all these models, ORS5, echo, Glorious 12, mismass, and HICOM. So you can see here there is a big differences in salinity starting 28 to 31 or 32. So you're looking at a 3 PSU difference sometime. So what I'm showing here, the circles are scissors. Scissors are, so most of the time scissor data is very close to the ORS5, right? So, and also you can see the BGP is here, and also the satellite data, because most of the times ice coverage, so you don't get, the satellite data. But you can see sometime, the overlap in the satellite. So basically the, ORS5 is in between, very close to the observations. That's what we are seeing here. So if you can also do the scatter diagram to see where you have more, outliers and all. So here you can see the SMOS and SMAP. And as I mentioned to you, SMOS covers Beaufort Gyre much better than SMAP, but you can see a lot of outliers in the, SMOS. And if you compare with the models, echo, mismass, and HICOM, you can see the echo and the HICOM are saltier than the, mismaps, so that's what you're seeing here. And also, if you compare with the, reanalysis, ORS5 and Glorious 12, Glorious 12 is saltier than the ORS5. And EN4 and BGP are, observations, so you can see, pretty close to best fit. And as I mentioned to you, we are also working on the Russian shelf area with Mike Steele. So you can see here, take this MOS, SMAP, and OISS. You can also see, the big differences in SMAP and, SMOS, where you have the lot of river runoff is there. As I mentioned to you, ORS5 reanalysis is a little bit better than other models. I know, again, I'm iterating reanalysis. This is not a model output, but if you take the differences, you can see the, the SMOS is a little bit more saline than the SMAP. So even for the Russian shelf area. So how these models compare with the scissors or EN4 with the depth. So you can see here, scissors, data is plotted here, EN4. If I take the differences, echo minus scissors and mismatch minus scissors and ORS5 and, glorious 12 and scissors, you can see pretty much, our same thing with EN4, that there is a big differences in salinity top 50 meters depth. That is layers you will see. It's interesting to see the mismap, even in the deeper layers is much saltier, like 0.5 to 1 PSU difference, in the even in the deeper layers. So ORS5 is, a little bit, very close to scissors and also EN4. So that's what we have seen in our, studies. So if you look at the freshwater content, as you know that 1/4 of the liquid freshwater content in the Arctic Ocean. So so the Beaufort Gyre region. So the Beaufort Gyre is Beaufort Gyre is very important for the freshwater content. So here you can see if you compare EN4, ECHO, MISMAP, ORS5, and Glorious 12, what we have seen is you can see the freshwater content in all the pretty spatial structures looks good, but when you look at the ECHO, it has less freshwater, almost you are seeing 16 to 17 meters, whereas the other models are doing a little bit higher freshwater content. So what about the trend? So yesterday we saw some talks on the freshwater trends in the Beaufort Gyre. So here I'm showing here the freshwater content, and the trend is here, and you can see the 1990 to 2006, and there is a jump here, and again it is jumping. So if you are using the ORS reanalysis, the reanalysis is showing the freshwater content is increasing in the Beaufort Gyre region. So you can see the rates are here. So the best fit you're looking at 0.2 kilometers per year. That's what you're looking from 1990 to 2018. And also you, oh gosh. I need to go here. And also what we have seen, this is, if you're looking at the 4 decades freshwater content trends, so if you're looking, so then you can see 78 to 88 and 89 to 98 and also 99 to 2008 and 2009 to 2018. If you're looking, what we are seeing is the Russian shelf area losing the fresh water, and Beaufort Gyre is gaining. The Russian shelf is decreasing the freshwater content, and Beaufort Gyre is increasing the freshwater content with these freshwater content trends. I need to go this way. And also, if you are looking at the new 2008, 2018 minus world 1979 to 2007 period, if you take the difference in salinity overlaid with the current anomalies, and also freshwater current content overlaid with the current anomalies, and you can see the trend in like this. What we are seeing is the strong currents we are seeing in the anticyclonic Beaufort Gyre region, the strong currents you are seeing here, and also we are seeing the transport from Lapland Sea, you are seeing to Eurasian Basin. That is very, you can see the strong trends, you can see which are very significant if you are taking from the difference from the new minus old. So that is significant. If you look at the current, surface currents are also much stronger in this during this time period. So just quickly, I want to touch about the Saildrones. If you take the Saildrone, path is here from JPL Saildrone, and if you are comparing the Saildrone with the SMOS and SMAP, the SMOS and SMAP is doing pretty good comparison with the Saildrone. Sometimes you see the peaks like this where the ice edges are there. But if you look at the spread, if you along the Saildrone track, if you're comparing SMOS and SMAP, then you will see the good correlation. SMOS and SMAP are very close for entire Arctic region. If you're looking at the BG region, also you will see, as I mentioned to you, SMOS coverage is much better in the BG region, so you will see good, much better fit in the SMOS than the SMAP. So in summary, satellite and in-situ restricted from the sea ice regions. So salinity is difficult to get, from satellites. And as I mentioned, SMOS, even though its coverage is better in the BG region, but SMAP is much accurate than the SMOS. And ORS-5 reanalysis is much better, in this region from our study. And again, you saw, HICOM and Glorious Toll are much saltier. So we need observations to compare, these models. So I hope that's what the message I'm giving from my talk. Great, thank you.
Thank you, Subra. We have time for one or two questions. I see Anne, you have your hand up.
Yeah, hi Subra, thanks for the nice talk. You can hear okay?
Yes, I can hear you.
I wanted to ask you, could you say a little bit about the uncertainty in the product, particularly in the Arctic, where you often has the problem, with when you have thin ice, for example, and also the comparison with the reanalysis versus a model that is running without the, well, depending on the methods that you're using, when you're comparing trends from different years, are you taking into account, for example, when there's data, potentially it looks different than when there's no data, and therefore potentially what you're seeing in the difference in trends could simply be due to the distribution of the data. And then my last question, I think if I could be wrong, but I think the satellite measures the skin sea surface, the skin salinity as compared to, for example, the model, which actually has a grid cell box of a certain depth. So do you also take that into account when you convert them?
Right. Okay. So first of all, whatever the comparisons I showed with the models, those are matching exactly scissors time period, 2012 to 2017. And the depth structure you are seeing, that is, along the scissors track. Right. So we haven't done much analysis in the Beaufort region beyond that transect. So I don't have the clear numbers or uncertainties to give you right now. So that is my first question. The second question you're asking, yes, so ORS-5, not only we looked in the Beaufort Gyre region, but in also rest of the Arctic, we looked at different places, and we felt that ORS-5 is much better, is more close to the observations compared with the models what we have used. We felt HICOM and ECHO are saltier. I think I covered your questions. And do you have any other questions?
No, I think I can have a discussion more offline as well to maybe to try to clarify some of the.
Okay, great, thanks.
Are there any other questions for Subra? Jamie?
Well, yeah, that was great, Subra. I had a thought when you were looking at freshwater content. You can also make an estimate of that from a comparison of altimetry with GRACE.
Right.
And is there any further effort going on in that direction?
Yeah, we haven't done, but that is another, work we need to do. Yeah. So look at the freshwater content trends. Yeah, that's, yeah. So as I mentioned to you, ORS 5 is showing the freshwater content trend is increasing. And yesterday I saw, I think Mary Louise was showing that there is a dip in the, down. And I don't know, where the difference is coming. Maybe we need to check with other models too, to see not just only ORS 5, what the other models are doing.
Yeah, I think we can move into our general discussion session. So thank you again, Subra. Patrick, I see you have your hand raised. Do you want to ask a question?
Actually, I was I was a bit worried that it might be too technical, but I'll ask Subra anyways. When you compare the reanalysis products, are you also comparing the analysis increments that give you an estimate of how much you're putting back the models to the observations? That seems to be important to do.
So that's a good question. So no, we haven't looked because I'm looking only we compared ORS 4 and ORS 5, right? But I felt ORS 5 is much better than ORS 4. So I don't know the differences. So what I felt only the fluxes are different, how they forced the reanalysis or something. But we haven't done much rigorous analysis on that. Yes, I agree. Yeah.
Okay, thank you.
Are there any other questions for anyone, any of the speakers from this session? Or more generally?
Thanks. This is Mary Louise again. I'm going to ask Ron another question. Sorry, about sea surface height and dynamic ocean topography. Are you, so you've told us that the sea surface height product is available now. Is there an effort also to get the dynamic ocean topography and geostrophic currents computed and archived online and put online?
Not the circulation, not the geostrophic circulation, but that's relatively straightforward if that's of interest. So so these monthly fields that we have of the ice covered ocean and the liquid ocean, they're not merged yet, but I think there's a move toward doing that. The fields, this is a little detail. The fields are, so for a given monthly field, we show basically, we archive, there's a record of the sea surface height from already different orbits. So you can get the daily observations and the monthly observations. So you can handle the, instead of doing, accepting the kind of average that we do, you can do your own weighting of the space and time, in space and time, if you like. Because obviously the orbits are not, it's sort of quasi average. It's not a real average over the entire month. those are available. And if anybody's interested in actually having us compute the circulation pattern as well, that could be done easily.
I think Ron, maybe if you correct me wrong, the Copernicus CMMs, they supply the ADT, absolute dynamic topography. The Copernicus, yeah, they do CMMs, they do the absolute dynamic topography. It is available for the Arctic.
Yeah, I think that's a recent product, and those are the products that we use in the comparison with ISAT-2. I think what she used was process, as far as based on what my understanding of her talk, that product was based on AVI processing, not the Copernicus data set.
For the online folks, the question was, is that what the product that Francesca was talking about?
Are you talking about I'm not sure if we are talking about the same product, because my product is not available on Siemens. I've uploaded it on Pangea. I think it's, there was a paper by Stina Rose, I think. And that's part of this climate change initiative, and that's a very long time series of sea-surface height available on Siemens, I think.
Yeah, Francesca, this is Ron. I believe the data set that you were using was from Ricker's processing. Is that correct? Rob Ricker?
Yeah, sure.
Yeah. Thank you.
That's true. Yeah.
Okay, John, I see you have your hand up.
Yeah, I have a question joint question for Ron and Ignatius. So Ignatius showed us that we're in trouble of losing good atmospheric sea level pressure measurements. So in light of, inverted barometer, what does that say about future sea surface height estimates? Are we just going to have to average over fluctuations in atmospheric pressure and hope they zero out, or just live with the fact that we have this uncertainty from atmospheric pressure?
I'm hoping we find ways to get more buoys out there, but yeah, short of logistics, that's definitely an issue we need to keep in mind.
Ron, any comment?
Yeah. Well, John, I believe you know this as well. And in shallow waters, the inverted barometer, the straightforward inverted barometer doesn't work that well. So that's something to keep in mind.
Any more questions, comments?
So just to continue that that thread with sea surface height and inverted barometer, like what do you actually do now to your returns? Do you do anything with respect using the atmosphere to correct your sea surface height or anything like this? No.
So in altimetry processing, there's a lot of stuff that's removed, that's systematic. For example, the atmosphere, the delay, but that's altimetry processing in terms of getting the right range. So in the SSH, we take out ocean tides and basically all the tides that are known, and the inverted barometer. and what else? There's a long list of tides and other geophysical effects that we systematically remove before we produce the SSH.
So where does this atmospheric pressure data come to do that correction?
Oh, sorry.
Hemisphere, you mean atmospheric pressure?
Yep.
The atmospheric pressure for ISAT-2 is from a model at Goddard called GEOS 5. And the way the inverted barometer is computed is the pressure at the point relative to the average pressure over the oceans from the sea level pressure field.
Right. So my point is,
Yeah.
you know, as Ignatius showed us, if you don't have any real atmospheric pressure data, your model can go off into never land. And so it's not just we're potentially losing out on atmospheric wind information, surface wind information. We're losing out possibly on sea surface height anomalies, right?
Yes, that's right.
Yeah,
So let's have more buoys out there.
exactly.
That's one thing we should advocate for that, right?
And can I ask a technical question? Do we know in the Arctic where we have sea level pressure variations that the ocean responds instantaneously to that via the inverted barometer? Or are we just making that assumption?
I think it's in other altimetric processing, we're making that assumption. I think there's, yeah. So the way it's done, it's instantaneous everywhere. But if you were interested in taking the instantaneous pressure and adding some sort of lag, that I think all the corrections are there for you to adjust. I guess that's the word.
I mean, geostrophy only cares about the horizontal pressure gradient, doesn't care where that pressure gradient comes from. It could be a gradient in atmospheric pressure, it could be a gradient in sea level. It's just total pressure. It's how you take sea surface height information and combine it with atmospheric pressure.
Francesca, I see your hand up.
Yeah, I just wanted to ask, what do you think about, okay, usually this atmospheric pressure is corrected for the global ocean with another correction, which is this dynamic atmospheric correction. Can you hear me? Yeah, so I don't, do you think that's worth using in the Arctic, or is still not a good correction for the Arctic? Do you have any idea? For Ron, the question was.
Actually, I didn't quite understand the question.
Yeah, so I think for the global ocean, the sea surface side is corrected rather with this dynamic atmospheric correction, which not only is not a simple inverted barometer, but
Yes.
also includes the effect of, let's say, remote wind, the response to remote wind and pressure forcing.
Okay, I think if I understood you correctly, you're asking me whether the wind stress, you asking about wind stress impact on the sea surface?
Yeah, whether do you think that's because
Okay, so there, yeah. So in some of low latitude and tropical oceans, there's, I forget the name of the model, that accounts for surface stress, especially near the coast. In the Arctic, there's a the model runs in the Arctic as well, and we've looked at that. But that model does not have an ice cover. So the impact of the ice mechanics and dynamics on the height field are somewhat different than using strict inverted barometer. So especially in shallow waters. So we've looked at those differences, and we don't quite understand initially what the impact of the ice cover is. So what we elected to do was not to use I forget the name of the model, to adjust for the heights. So we opted to use inverted barometer as everybody uses for the open ocean.
Okay, thanks.
Hi, I'm going to interject something. Yeah, the ISAT-2 open ocean product uses uses the model that Ron can't remember the name of, and I can't either. But it's a full dynamic model that that takes into account other things besides inverted barometer, and I've kind of looked at it in comparison to what's just the inverted barometer in the ice-covered regions, and in comparison to the model that's basically a modified model that's used for the ice product. And they're, as Ron said, they're not very different out in the middle of the ocean, but they differ more as you get in close to shore.
Thanks.
I guess one piece of reassuring evidence to this is, at least in the central basins, the bottom pressure measurements bear no relationship to the local atmospheric pressure fluctuations, meaning that as soon as the atmospheric pressure changes, the sea level pressure changes, at least in the central basins. So that's hopeful. The ocean bottom pressure changes don't have any relationship to the atmospheric pressure changes overlying the mooring, meaning that there's an efficient inverted barometer effect.
I think there was I forget, it's been a long time. Cecilia, you remember that? We showed the bottom pressure and the altimetry in one of the papers, right?
I think what Marie says is right. Like, at least I've been looking a lot at the mooring, at the bottom pressure data in the Beaufort and at the North Pole. And yeah, I think I had mentioned this to John yesterday. The fluctuations of the atmosphere, instantaneous fluctuation of the sea level pressure, assuming those are the best we can get from on top of those moorings, are accurate. The actual fluctuation of the bottom pressure was not affected by these changes in the surface. Like, that was much more smaller than what we actually see at the bottom. Yeah, so yeah, I think you're in the right. For the coasts, yeah, that's a worrisome situation.
Wait. Oh.
So the coast, the sea level pressure field isn't as bad since we have a lot of land stations along the rim. It's just like away from the coast and over the central ocean.
Cecilia here. Then we don't have to worry about.
Okay, if there's no more comments, I think we've come near the end of our time for this discussion. Jamie, do you have any final comments?
No, I'm fine.
Yeah. So now we'll break. I'm nothing without my agenda. Yeah, so now we will break until 10:30 when we'll start our next session. Thank you, everybody.
Okay, I guess it's time to start up again. Okay, our next speaker is Nan-Hsun Chi from NOAA PMEL, and she's going to, as you can see, talk about Saildrone USVs to validate Oscar surface currents in the Western Arctic Marginal Sea.
Hi everyone, my name is Nan. The title is using Saildrone unmanned surface vehicles to validate Oscar surface currents in the Western Arctic Marginal Seas. I'm a PMEL postdoc working with Dongsha and Qidong. These are the three Saildrones. The three Saildrones in 2019. So we all know that this area undergoes large seasonal variations and sensitive to warming climate. One of the most challenging places, but it's very critical to observe in the North Ocean because of the sea ice. As you can see, one of the Saildrones was stuck periodically in the ice, but managed to come out. And the shallow depths, so it made it difficult for a lot of ships to make complete surveys. So these solar powered and entirely wind propelled vehicles provide a very unique opportunity to look at this area, and then also can have a chance to validate the Oscar satellite derived surface currents. So comparing the two, when the Oscar, the final version is a 1/4 degree, 1-day resolution, and looking at about 15-meter depth. It's a satellite-derived currents product using surface height, vector winds, and SST from various satellite products and in-situ observations. And the modified formulation combines geostrophic, Ekman, and thermal wind dynamics. Saildrone currents are obtained from 2 Saildrones in 2018 and 3 Saildrones in 2019. They are all in summertime. A long track is 5 minutes, so they turn for the ATCP current data that I'm using. They're turning on 300 seconds and turning off another 300 seconds, so basically taking that. And the mean vehicle speed is about 1 meter per second. So it travels about like 80 kilometers a day. So which is usually it would goes a few grid points of the Oscar. So at the 300 kilohertz ADCP, it's downward looking, and it gets 4 meter to up to like around 100-meter depths, depending on the topography and the echo intensity. This data, so I QC them and detide, so you won't see, supposedly know the tide in the data. So these are the 6 Saildrones during 2019, colored by salinity and temperature. So in May 15, 6 of them just released here, and one of them stayed all the way in Bering Sea, and then the others all went north and past places near the Yukon River. You see some like warm, fresh water, surface waters, and then in June 5th, it crosses the Bering Strait, and then they went northward, staying most of about like a month or so in the Chukchi Shelf, and in late July, they crosses the slope and made another stay another few weeks in Beaufort Sea, and before they came back. So that's what they look like. And in 2018, the two Saildrones have similar tracks, but they didn't go to the Beaufort Sea. So here I will be showing more about the 2019 results. This is the middle panel is the 3 Saildrone along track data colored by the salinity. And these 3, sometimes you see like strong currents like the Bering Sea and then the Bear Canyon and the Chukchi slope current. And on the top panel is the corresponding Oscar data. And this is the vector differences, Saildrone minus Oscar and colored by temperature. But in order to compare them in a more aligned spatial temporal resolution, so it will look like this. So this is, later on, I will show you the results from these. So actually, because it's a quarter degree one day and we want to match it, but actually the Saildrones, every data here is about at least a few hours of average on the quarter degree. And this is the wind rose plot for the collocated vectors in wind speed, current speed of Oscar, current speed of Saildrones, and their vector correlation. And the different colors is the speed, current speed here, and this is in degree or their cosine. So Saildrones in general, they are larger than Oscar with an average difference about order of 10 centimeter per second. I would like to look at different like regimes, like stronger current regimes, and then look at some fresh cold places to see if in certain regimes they have better correlation, has little differences, or has vice versa. So first of all, if I look at where the temperature is smaller than 2 degrees, salinity smaller than 27 PSU, like a lot of them are either in Beaufort Sea or a few places on the shelf that near the ice melts. The vector correlation is a lot worse. I would assume that, so we know that the Oscar data, they do not use salinity information for the buoyancy part. So I wonder if that's, maybe that's why the correlation is not very good. You can see that their distribution is pretty different. In the Bering Strait, like in the stronger current regimes, the vector correlation is pretty good, but the current speed is different. Now, average about 20-ish centimeter per second. So it's larger differences. Also want to show you 2 maps of one in upstream the Bear Canyon to see how the current look like, and another one in Chukchi slope current. So this is the canyon here. This is the gridded Oscar data, and then this is the Saildrone 5-minute data. So overall, they're all going north, both are going northeastward to eastward, and then it increases towards the Canyon or the Alaska, the coast. So the big pictures looks okay. And the Chakchi slope here is that it's going northwestward and it's less intense, and then it has some like direction, opposite directions on the shelf. So basically, the big picture looks okay, but the speed differences can be seen. And this is to summarize what we see near the Bear Canyon and Chakchi Slope current. Similar to Bering Strait, their vector correlation is pretty high, but the current speed is larger for the Saildrones, also around 20 centimeter per second. So this is a statistic between Oscar and the Saildrone data, looking at similar spatial temporal resolutions. So overall, the Oscar is about 5 centimeters per second smaller, RMSD about 10 centimeters per second, and more than 70% of them have positive, relatively okay correlation. For the stronger currents, their vector correlation is better, but their biases is larger. And rooming square current difference speed is also larger. For the weaker current regimes, we expect them to be smaller, but their current vector correlation is not as good. For the cold, fresh surface waters, their current vector correlation is the worst. It's more than half of the collocated vectors. They're either orthogonal to each other or negatively correlated, with bias about 3 centimeters per second and RMSD 8 centimeters per second. So here present rarely measured the upper ocean measurements from the Saildrone uncrewed surface vehicles in Bering Sea, Chakchi Sea, and Beaufort Sea. So the overall speed difference for the collocated Oscar and the Saildrones is notable, with Oscar smaller than Saildrones by an order of 10 centimeters per second. We can see large difference, but it's very high correlation. Often occurs for stronger currents, like in the Bering Strait, upstream Bear Canyon or Chakchi Slope current, and some places near the very steep topography. The low vector correlation is often observed for weaker currents and at the cold fresh regimes. So this preliminary study serves as a benchmark to understand the uncertainty of the future studies, as I would like to explore the feasibility of combining Oscar and satellite temperature salinity to investigate the surface Pacific water inflow. And thank you. Hi.
Check.
Yeah. So I have a question on the Oscar currents. So Oscar uses the regular altimetry data. It's not included the sea surface height from cryosat or ISAT. I'm really surprised, how these currents are with Oscar. But your talk looks, Oscar is doing good in Arctic.
Yeah. Sir, is that a question or a comment? Sorry.
Well, it's a comment, but also so do you know any, the version 2 you are using, maybe they are using ISAT-2 or cryosat, or is there any difference, regular Oscar data and this data?
So this Oscar data, I don't know like exactly what the satellites that they use. And this version is relatively new. So I don't know enough to answer your question about like Oscar itself. Like, I'm still like looking into it.
I have a quick question on the biases between the Oscar and the Saildrone data. I know you showed that the high-speed region versus low-speed regions, but in terms of the spatial, like shallow region versus deeper, have you looked at the biases between two areas?
I haven't. So what let me show you a map. So most of them are on the shelf, so they're relatively shallow, but I haven't compared those here and here. That's where you get to the like the deeper. Is that what you mean, like on the shelf or not on the shelf?
That's correct. For example, the Alaskan coastal currents region versus slightly offshore. So is there where the highest biases are shown in the Oscar?
I haven't, but I will. This is also I'm doing that as well, but this is kind of I'm in the middle of doing the analysis, so I'm just showing like some of them.
Hi, I wanted to comment on Subra's question. As far as I know, Oscar uses spectrometer winds to estimate the wind-driven component of the surface currents. So that's why I'm not surprised there is a good correlation between Oscar and Saildrone observations, because it's mostly wind-driven.
The geostrict part is coming still from regular altimetry. So I think the wind-driven part is taken care of where you are getting good comparison with Saildrone. That good.
I'll give the final comment to Ben Roth online.
Yeah, I'm Ben Rabi from ABI. Just a question, how much effort was it in the field to run those Saildrones? Was that formidable or was it not so difficult? Would you like to comment?
Do you mean that how difficult is it to run Saildrones? Is that the question?
Yeah, exactly. How were your field operations? Would you say that's quite difficult? You can't do it a lot, or is that something you could envisage in different parts of the Arctic and people could include it in their regular field work?
Okay. So the Saildrones, I'm not sure, like I wasn't involved in this mission. Do you have any comments?
Okay, no, thanks.
Well, first, I'd like, you can finish if you have any comments.
So I know that all of 6 Saildrones, they managed to come back in one piece. And they did stock in the ice. A few of them did stock in the ice multiple times, and they were managed to come out. But that's like this kind of ice. But I'm not sure it would survive in all kinds of situations. And they need wind to move. If wind is not an issue, then they usually can go at about 10 to 20% of the wind speed. And it requires like pilots to intentionally kind of guide them. I wouldn't say it's very easy, but they managed to stay in this kind of difficult places and also under the hurricanes. And like they managed to stay in this challenging places, but I'm not sure. I don't think they have put it in the central Arctic where their ice may not be like this. And then a lot of time they sail without eyes. So yeah, that's.
Hey, Ben, it's Mike Steele. So PMEL has been doing the Saildrone expeditions up to the, say, Alaskan Arctic for a few years now. In 2019, it was a collaboration between a project sponsored by NASA called MIST-3, focused on sea surface temperature. So two of the Saildrones that were just discussed in 2019 were I was involved with that project. And then we sailed two more in 2021, and there's two right now doing the DBO lines, the Distributed Biological Observatory lines. And let's see. So yes, there is a picture of a Saildrone in ice, and I was surprised in 2019 how brave Saildrone was. So I should back up. You can't buy a Saildrone. You can't buy a Saildrone. You can lease a Saildrone. They have a mission control. You tell them where you want it to go. They make it go there, and then they have the Saildrone at the end of the expedition. They're really good to work with, but that's the model. One of the Saildrones was damaged and managed to limp back to Barrow, where it was recovered. After 2019, we asked them in 2021 and 2022 this year, how about going back to the ice? And they're like, no. So at the moment, they're not really happy about being near ice, but that could change.
Okay, so yeah, as before, feel free to raise your hand if you're online or if you're in person.
I'll kind of start things off. Comment and a question for Sylvia. The comment is really nice talk. And the question, kind of two questions. One, I guess it's a matter of terminology. For a long time, people would search for eddies, and they were talking about really distinct eddies with high energy. But my sense is that we're talking here about basically horizontal turbulence and generalized energy that's in those turbulent motions. Is that what we're talking about?
So I am trying to talk in a sensible way about the entire range of eddies that you might encounter. And when we see a velocity section, the most energetic sort of closed contour, small scale eddies are the features that stand out. But then there's a whole sort of other range of, if I go talk to modelers or theoreticians, they want to tell me about the meanders, and the meanders doing things to the gyre. And so I said, okay, let me try and look for these meanders or for the closed eddies, to what extent can I separate them in the data? What stands out? And I think if those meanders are sort of there, I think they're lower energy. They're not so easy to separate out from the smaller closed contoured features. But they aren't something that we routinely sort of look for in the data. And so I did try to do that. I don't know if that answers your question or not.
I think so. I think it was more, yeah. I mean, I remember a couple of studies where people were trying to find eddies that, you could identify the whole circulation, and these were isolated eddies that would propagate, and they have core velocities of 25 centimeters a second or something like that. So I think I understand. The other one was kind of a detailed question. When I look at the raw plots, I think, oh, there's a lot of ice velocity that shows up in the velocities below the picnic line, and which is okay, but I also think that the velocities, if you're trying to look certainly at absolute velocities, they're pretty sensitive to direction errors because the velocity of the ice is so high compared to the absolute velocity of the water. Is there a way to kind of counteract that, or is the processing make it not an issue?
So it's a valid question to ask if the processing is good enough to look at this. And I would argue because we're on a drifting platform, it makes it really easy to tell if we've got the processing wrong. And in that sense, I think we do see, that this is a robust signal, I guess would be my answer. That because we see this sort of decay with depth in the mean field, it's not just a directional error in the processing. Certainly, it's something I can take more of a look at and do a few more statistics with. But
Yeah, Jamie, you're right that to measure absolute velocity, we have to subtract the ice velocity from the relative velocity. The ITPV has an IMU in it, and we're doing our best job to get orientation, taking into account the tilt of the wire and everything else. And the proof is in the eating, right?
Yeah, well, I mean, I guess I'm not sure how the what do I say? How the statistics of the absolute ice motion and the uncertainty in the direction calculation figure into it. But it seems like that would be kind of easy to assess and come up with a number for. Anyway.
Can I, sorry.
Can you, sure.
Can I ask a question, another question, or are we not? Was somebody online going to say something? This is Mary Louise.
I think it's up to you.
Okay, this is the same thread at least, and this is for Sylvia. So some years ago, my student partitioned kinetic energy by first doing what John actually described earlier, and which is splitting the water column up into dynamic modes based on discretizing the stratification so that and looking at how the stratified water column moves, the different types of motion in that. And then you can write the kinetic energy as a sum of those modes and get coefficients in front. So that's one way to partition the energy. And it might be interesting, there might be interesting relationships to your methodology, because one thing that you can do with the dynamic modes is each mode has a horizontal length scale associated with it. So the first mode, for example, the first baroclinic deformation radius and so on, so that then you could somehow, start from these horizontal length scales, assuming balanced motions, say, which could be potentially quite interesting.
Yeah, I mean, I'll agree that you could certainly take a modal view of this, and I have not done that. I've simply said this is the data, and this is one way I can partition it. And I mean, I guess it's just a different way of looking at the observations. I don't know what the relationship to a horizontal scale and that modal theory would show.
Yeah. One interesting thing is in the mid latitudes, this is something that Carl Wunsch showed years ago, that the dominant motions are surface intensified. But then that's very different from the Arctic, where most of the eddy kinetic energy, as you showed us in your talk, is concentrated in the halicline. And this is the first baroclinic mode, and that has interesting implications for energy dissipation. But anyway, it's just a comment. Thanks.
Ben, I saw you had your hand up for a minute, but do you still want to?
Just a very quick one, coming back to the velocity and the compass. I can see that there are people who have looked really strongly into these compasses and get much more out of them than people generally do. I wonder, have you ever compared to like a shipboard ADCP, just to see if you you got that right, say a different drift or something?
We haven't compared to a shipboard ADCP. The thing I have compared to is, I can take a look at the VJOS mooring velocity and say, do I have similar statistics? And it's a mooring, so I can't exactly do the same spatial scale separation. But we can compare to that in some ways, and it is similar enough that I don't think I have significant errors. If you want me to be honest, if anything, I would tell you the mooring could use a little bit more processing. But that's a different subject.
Understand.
Any other questions or comments for any of our speakers?
Yeah, just a question to about the energy decomposition and related to the size of eddies. In previous observation, I mean, the student from Louisa mentioned in that observation, to my knowledge, according to the literature, there are not so many large eddies. So in your talk, Syria, you decompose the energy to really a large range. I think this touched in previous discussion that the larger one, like few hundred kilometers, can be considered as a large mean or the mean energy. But even that, if you go down to the relatively smaller range, so do you think they are really close eddy energy, or still a larger part of some meters just with a little larger spatial scales? So to me, I still cannot connect the observation-based knowledge on the size of eddies and now the spatial scale that you have chosen to do the decomposition.
Yes, I think I agree with what you said, if I understood it correctly. Yeah, okay, I'll leave it at that.
Any further questions or comments? In person or online?
I had a couple of things, Jamie. One, I looked it up. The dynamic atmospheric correction we use for the open ocean ISAT 2 is the 6-hour Aviso MOG 2D. So Ron and I couldn't remember the name of it, but that's it. I looked it up. I had a little question for Nan-Hsun about the sail drones. It went up Bering Strait, and did it stay on the U.S. side of the border?
Yes.
Oh, okay. They have the operators have some criteria that they wouldn't cross, I guess. Okay. Any other questions? Comments? Well, I guess we're ready to eat.
Yeah, seeing no response in the room, we can take our lunch break now. Okay, everybody, we're going to get started with the lightning poster talks in a minute here. For your information and for the presenters' information, we're going to be running off of one slide deck. So I'll just call your name and you can come up and click through your slides. First up, we have Lauren Hoffman. You can use this down arrow if you want.
Cool. Hello, I am Lauren Hoffman, and I'll be talking about some of the work I've been doing with my collaborators listed here on using machine learning as a tool to both predict and understand ice motion in the Arctic. So as far as predictability goes, we're going the machine learning route because these models are more computationally efficient than these physics-based dynamical models. And essentially what we're doing is we're taking making one-day predictions of ice velocity from previous day ice velocity, previous day ice concentration, and present-day wind velocity. And so we'll take that and look at a few different models. As far as understanding ice motion, as the ice melts, its response to its forcing is changing. In particular, I said we're using wind speed as a predictor, and it's becoming more responsive to the wind forcing. On the bottom here, we're showing the wind factor, or the ratio of ice speed to wind speed, and we find that that's increasing. And so we'll try to use the machine learning to look into that more and see if we can find out why. Some of the results we've got so far as predictability goes, the line plot here is looking at the seasonality of the correlation, or a metric of the skill of 3 different models. The CNN, a neural network, in blue, which outperforms a linear regression model in green, and persistence, as we would hope, in yellow. We do see a little bit of seasonality here. We see slight decreases in that skill during these times of maximum and minimum sea ice extent, or when things are changing a lot. So one of the questions is kind of what's going on here. And then if we move over to the maps, we're looking at, the first one is the correlation, again, that metric of skill for the CNN model, the neural network. And the second one is the correlation difference between the CNN and the linear regression, where red indicates areas where the neural network outperformed linear regression. So for the most part, our neural network is doing really well, and it's outperforming linear regression, except for in some of these coastal areas that I've circled here. So what's going on coastally is the question. And so that's as far as predictability. We've made models that can make skillful predictions. As far as understanding the ice motion, the 3 maps at the bottom here, we're just looking at the linear regression parameters at each grid point throughout the Arctic. And so we can see which one of those inputs to the model were relevant at what areas. Clearly here we see wind speed has the highest relevance in predicting that ice velocity. Again, we're on 1-day time scales, so that makes sense. But in the future, we hope to get similar outputs of these from the machine learning model using explainable AI. And whereas linear regression, we get one of these for the entirety of the time series, for explainable AI methods, you can get one of these for each day you make a prediction. So we'll have one of these maps for every day from 1992 to 2017, so we can kind of see how is that relevance of the wind changing over time, how is the relevance of these other parameters changing over time. Email us here. Thanks for listening. Yeah.
Excellent. Next up, we have, I think this is Marian's, right? For some reason, your name got very small. Oh, at least your email's down there.
And apparently the wrong version because the titles are all the same. Anyways, so my name is Marian Alberti. I'm a postdoc at Princeton University, and this is work I've been doing with Mary Louise Timmermans, Sonia Legg, and Bob Hellberg, who are at Yale, Princeton, and NOAA GFDL, respectively. And so this is some preliminary results trying to evaluate GFDL, a suite of GFDL models for calculating heat budgets in the Western Arctic. And so the scientific motivation and kind of long-term goal of this project is to really understand the role that the Kowk GC plays in modulating the heat transport from the Pacific Ocean that's subducted into the warm halocline of the Beaufort Gyre, and looking at this on seasonal timescales. So what we're looking at right now, so you can see this diagram in a very kind of naive cartoon where you have the heat coming in from the Bering, or coming in through the Bering Strait from the Pacific Ocean, going over the Chukchi shelf where there's lots of interactions with the surface, so both the sea ice and the atmosphere. And that Q surface term changes seasonally and in a way that that's not well constrained by all the available observations. And that's really what's controlling, those two terms together control what gets out into the Beaufort Sea subducted under the surface mix layer. And so what I have at my poster to show you today is just some preliminary evaluations of a coarse and a high resolution coupled climate model that comes out of GFDL. And so on the left, what we see here is just a little table where we've made a comparison with the available mooring observations and observational products from those mooring observations to show that in general, where our estimates are within the observational error estimates for total transport on annual timescales of both heat and volume. And we're getting the phasing of the seasonal cycle approximately correct in our simulations, and we have some real improvements that come through the high resolution configuration that we're working with right now, mostly in our ability to represent the seasonal variability of the Alaskan coastal current. And then we're just starting to push into trying to evaluate the surface fluxes in our model and comparing those with ERA 5 estimates. And so we just have some preliminary wind speed biases that we're showing in the poster today. And the main takeaway is that for all the available simulations, both pre-industrial and historical runs, we get reasonably small biases in summer when we might expect surface heat fluxes to be influenced by the wind. So lots of promising comparisons between observations and models so far, and I'd be really inclined to get people's suggestions for other observational products we should be considering as we try to evaluate the quality of our models in the Arctic. So thank you.
Next up, we have Johannes Koling.
Hi, everyone. My name is Johannes Koling. I'm a postdoc at Dalhousie University in Canada. And I guess I didn't really list any of my co-authors here, but just for completeness, it's Doug Wallace, Dasha Atamanchuk, Johannes Carstensen. I think most of you probably don't know me, and the reason why most of you don't know me is that I actually do work a little more downstream from what has been discussed mostly during this workshop, so in the Labrador Sea. And in particular, I've been looking at the role, well, not the role, but the processes controlling oxygen export from the Labrador Sea, which we care about because that's a region where deep convection happens. Labrador seawater is formed, so the signal from the surface is mixed down and the deep ocean is ventilated. And we wanted to know how that actually relates to what then flows out of the basin through the 53 North Array, which I've marked in the very simplified schematic on the left. And the top right shows section plots of the 53 North moorings. It shows where the sensors are, and so at 600 meters depth are the ones that I'm using, which is near the core of the Labrador seawater layer, which is very high in oxygen. And then the bottom right figure kind of shows the main result of this study, which we also recently published, which is maybe a bit involved to explain that figure in detail right now, but essentially it just shows an annual cycle of oxygen, and the purple color shows that Labrador seawater is injected into the boundary current in summer, increases the oxygen concentration, and then gets exported, and that leads to an increase in the oxygen export of about 1.6 teramoles a year. And then to kind of relate that a bit more to what people here are working on. So if you look again at the section plot, you see it's very blue near the surface in the salinity and very purple in the oxygen. So that's because it's also very cold, and cold water can take up a lot of oxygen. And so that obviously is water that ultimately is of Arctic origin. And so on the left now, I'm showing a figure which I believe is from Shang Wang's paper, where I again mark the convection region that I'm studying. This is the green circle. And so you can see from kind of this Arctic circulation map that ultimately some of the water that is in the boundary current in the Labrador Sea comes from the Arctic through Davis Strait and through Fram Strait, And then on the right-hand side, I'm showing part of our analysis that we did in the paper, which also agrees with earlier results, which is that there's also convection happening within the boundary current, not just in the interior, which is kind of what people traditionally think. And so this Arctic fresh water that comes in, which is also high in oxygen, becomes part of Labrador seawater. We don't fully know yet to what extent or how important it is, but some of that will get mixed down. And so some of the oxygen that may get taken up in the Arctic would also make its way into Labrador seawater. And so I guess I have kind of two motivations for being at this workshop. One is for me to better understand what happens in the Arctic and how that affects what I'm studying. The other one is to say if anyone feels motivated to add oxygen measurements anywhere in the Arctic or in the outflows from the Arctic to the subpolar North Atlantic, that would be very interesting to kind of our community that I'm doing work in the biogeochemical cycles in the subpolar North Atlantic. And yeah, if anyone has any questions, feel free to email me, or if you're at the meeting, talk to me at my poster. Well, we can walk over to the poster if you feel so inclined, or just chat with me in general. Thanks.
Thank you. Next up, we have Marta Umbert.
For having me. So in my poster, I present a collaborative study with colleagues from NERSC and from the Marine Institute Sciences in Barcelona. And we do a 3D reconstruction of the upper ocean dynamics using only surface information. And to do that, we use the surface quasi-geostrophic approach, giving as an input surface data from the model. So we do a reconstruction from sea surface height, a reconstruction from buoyancy that is derived from salinity and temperature. We get the density, and from there we have the buoyancy. And also reconstruction from surface velocities. And this surface quasi-geostrophic approach allows us to have the stream function at each depth using a Prandtl ratio that is like this exponential function that depends on the stratification of the water column. And we do it in the Beaufort Sea and in Nordic seas. And here we see some results along the section in Fram Strait for the reconstruction of sea surface height, buoyancy, and sea surface velocity. And we compare these reconstructions against geostrophic and total velocity of the model. And we can see that there are some mesoscale structures as this eddy that is better reconstructed when using sea surface height or surface velocity, and that is not working when reconstructing from buoyancy. And in the panel that is in the bottom left, we can see the correlation between the reconstructions of sea surface height and the geostrophic velocity. And we see that they are quite good with correlation coefficients higher than 0.8 up to 400 meters, and that we reconstructed better in the months of winter and spring when the water column is more mixed than in summer and spring. And if in the other plot, the bottom right, sorry, is the correlation of the reconstruction from surface velocity and the total velocity from the model. And also we find that they are quite good up to 400 meters. So we prove, let's say, that with this approach, we can reconstruct only with surface data, quite good the upper ocean dynamics up to 400 meters. And this gives us the opportunity to apply it with altimetric data. And that is our next step. So thank you. And if you have any questions, you can just talk to me or write me an email.
Great. Next up, we have Xinyu Li.
And hi everyone, my name is Xinyue, and I'm now a PhD student from Alfred Wegener Institute in Germany. And today I want to talk about a topic towards understanding future development of Arctic Ocean using FASM2 model. And this is also the topic of my PhD project. And I plan to using a relatively higher resolution model to look into the future change of the Arctic Ocean. And we plan to address this relatively higher resolution model is because we want to look at especially the mesoscale eddies inside the Arctic in the future, because currently most of the CMIP6 and CMIP5 model are just 1 degree resolution, so that it is really hard to capture the eddy performance. And also for the satellite altimetry, this kind of data set, we don't have too long time scale and too long time period, so that it's really hard to understand all the things. And so that this is one of the simulation for a 4.5 kilometer resolution inside the Arctic Ocean. And I would like to give you some of the perspective of the future Arctic Ocean, but maybe this is not the final answer of the Arctic. The picture on the left is the CX extent, and I guess all of you have already known that the CS is decreasing from the past, and it is intend to decrease continuously in the future. And it is one thing is interesting is the blue line and shows the observational data set of summertime. And for the model, it is underestimate the decreasing trend of CS somehow. And this thing also happened in most of the CMIP6 data, and a lot of articles said that and maybe it is because of the underestimate of the eddy performance inside most of the model. So I guess maybe I still need to increase, minimize my resolution to see if I can get better result. And the picture on the right is the sea surface height, and I choose 3 time period, the historical time period, midterm future, and at the end of this century, and all of them are 20 years average. And I don't know if you can see it really clearly. And in this picture, you can find the Beaufort Gyre is enhanced in the future. And it means that maybe in the future, there are a lot of things are changing. And for example, the freshwater flux, the CS, and also in the anticyclonic geographic circulation, they might change in the future so that we get this picture, the Beaufort Gyre is enhanced in the future. There are a lot of mechanisms inside. So this is one of the storyline. And another thing is a small scale signal of this model. And the picture, the picture of the top panel is a recent article. It shows the strong relationship between the CS and the velocity. And the velocity is something related to the eddy performance. And it means that CS and eddies are highly correlated. And the picture here is the result from our model, and it is ocean vorticity. And you can see that in the future, the vorticity is somehow enhanced. And we can look back, the CS is declining so much, and we don't have too much summer CS in the end of this future. And so that we think that maybe because there are not so much CS at the ocean surface in the future, so that it is expected to have more CS, to have more ocean eddy activities if we look into the future. So that this is the result of this models. Maybe in the future, we will look into more details, for example, the velocity field. And also we will try to use a 1 kilometer resolution model to get much better results and understanding of ocean eddies.
Next up is Yeonju.
Hello, I'm Yunju from the Naval Postgraduate School. I didn't expect that small font size in the screen, but it was big in my screen. Sorry about that. So we have looked at the 5, different model types from the 1 degree CESM low resolution to higher degree CESM resolution, which covers about 5 kilometers in the Arctic, and also our in-house the regional Arctic system model equivalent to the CESM from 1 degree to up to 2 kilometers in the Arctic. So based on the 5 simulations, we calculated how much water coming through the major Arctic gateways from Bering Strait, Bering Sea opening, and the Davy Strait. The numbers are here quite different from the sets of simulation to another. But for our modeling community, we are kind of in a confident to go into the right direction, because in the high resolution simulations tend to show the more of volume fluxes into the Arctic and the more heat fluxes into the Arctic. But we still need a better estimate from the observational study to constrain the model to understand it better. So right now, it's challenging is that we know how much the water from the studies, from the published work, how much the water going through those gateways. But when you combine them, there's still imbalance of the 1 spectrops in the observational study. So there might be a hint in our analysis that what is missing in the observational estimate. But even from the high resolution models, for example, we have 200 terawatts of the heat going into the Arctic. Is that big enough or is that small enough? It may be too much in this setup, because in the upper left panel, we're showing the sea ice extent comparing with the NSIDC data. One of the CSM high resolution model shows that ice will disappear 2002 in the summertime. So it certainly indicates that the 200 terawatts, the heat into the Arctic made too much, or there's too much melting from the atmospheric models. We're not so sure about it. But the truth is, we believe somewhere in between. And also, when we look at the Bering Sea opening fluxes, the 1 degree model resolution versus, let's say, 9 kilometer resolution, we clearly see the strong currents along the Norwegian coast, which is the left-hand side, all the way. The left-hand side panel is the Bering Sea opening from the Norwegian side to the Svalbard. So most of the observational study sometimes often neglects the coastal currents, but the model indicates about 1 spectrops. So the imbalance in the observational study-based estimate might stem from those coastal currents, which bring a lot of the volume as well as heat into the Arctic. Thank you.
All right, and we're planning to have 1 virtual lightning poster talk, but Igor, are you there? I don't see your name on the participant list.
I will represent Rigor today.
Oh, excellent. Okay, just let me know when you want to advance slides.
Okay.
Yeah, we can start whenever.
Do you see my screen?
Oh, yes. Let me fix this really quick.
Okay. Do you see my presentation?
Yes. you can start.
Okay. Okay. I will present this poster instead of Rigor. My name is Andrei Pnushkov, and I'm also from the University of Alaska Fairbanks. And this poster generally summarizes observational efforts led by the Nan-Hsun and Amundsen Basin Observational System Program, or NABOS, over the last 20 years, in collaboration with many institutions from 18 countries. The NABOS project started in 2002 with a focus on the thermal state of the Atlantic water layer in the Eastern Arctic Ocean. This slide with Atlantic water temperature section illustrates how our repeated observation in strategically important locations helped detect an anomalous state of the Arctic. Specifically, these observations revealed more than 1 degree Celsius temperature anomaly in the core of Atlantic water comparing to the state of Atlantic water in 1970s. And they also helped understand how this anomaly propagated along the continental slope from Front Strait to the Canadian basin. Our next step was focused on how this advective anomaly associated with Atlantic water inflow affect heat fluxes and how they impact sea ice. In that, our finding of Atlantification was the key. In that context, Atlantification means weakening of stratification and increased vertical mixing due to enhanced winter ventilation. This process also include enhanced ocean-atmosphere interaction, which resulted in stronger coupling between sea ice, ocean, and atmosphere. To quantify the essential role of stratification, our next step was focused on the role of fresh water in establishing a barrier between the Atlantic water heat and sea ice. For that, we need to understand and trace freshwater sources in the Eurasian basin and to quantify their connection to atmospheric circulation. To answer this and many other questions, we launched a new stage of NABOS project. And this slide illustrates the configuration of moorings deployed in 2021 for monitoring freshwater redistribution between the Eurasian and Makarov basins. However, the current situation in Ukraine affects our plans for future NABOS program. Specifically, we experience a problem with finding a ship that can be used for our next cruise in 2023, because we need to find any alternative ship to the Russian ship that we used before. And we probably may need help from the United States and probably from broader international community to address this problem. And from a broader perspective, we probably need a dedicated United States icebreaker, which would be capable of doing science and doing research in the condition of the Central Arctic. And here is just several conclusions regarding this poster. And so, thank you.